we move on to the conversion of non-deterministic finite automata to regular expressions. So given a non-deterministic finite automata, as we are given one here, what is a regular expression that describes the language that this automaton accepts, right? So there are multiple ways to do this. One of the ways that I prefer doing it, which is easier and quicker, is using the following logic. So for any particular pair of states, let's take Qi and Qj, right? So for any two states, we have a regular expression that is accepted for paths that go from Qi to Qj. So you have a regular expression that is accepted. Now, if there is another state Qrip, right, through which you can go to get to Qj, then from Qi to Qrip, similarly, you will have a regular expression that is accepted. Let's call it R1. And possibly you can have a regular expression labeling paths that go from Qrip back to Qrip. Let's call this R2. And then you have regular expression labeling the paths from Qrip to Qj. Call this R3. Right? So let's call this R4. So R4. So please note that this is not a single edge. It could be a single edge, but it could also be more than one edge. As you have seen that a single regular expression translates to more than one state in the finite automata with many transitions possibly. So R4 here could be a combination of sequence of transitions taking you from Qi to Qj, not going through Qrip. But you could have a path through Qrip which is labeled as R1 followed by some number of occurrences of R2 followed by R3. So the regular expression that describes all paths from Qi to Qj would be expressed as R4, right? Or that is the union. Sometimes we use plus instead of union, so the alternate way is R4 plus R1 concatenated with R2 the whole star, that is the clean closure, in also alternatively written as R2 star, followed by R3, right? So this is the regular expression that describes all paths that take you from Qi to Qj through states labeled other than Qrip and through Qrip. What is Qrip? Qrip is a state that we are going to rip out of the system. If we rip the state out of the system, we will also lose all paths that go from Qi to Qj through Qrip. So we need to add the regular expression R1, R2, R3 on a transition from Qi to Qj. So we add R1, R2 star, R3 on this transition. Right? This is a dummy transition. So let's see how this works with an example. So with the given NFA, we will convert it into a regular expression. The first thing we do is we add a dummy start state and a dummy final state. So we have an epsilon transition connecting the dummy start state with the actual start state, and an epsilon transition connecting the final state to the dummy final state. The rest is copied as is. Now, if we choose to delete any state, it must be a state which is from the original finite automata. So let us look at deleting the state labeled 1. So if we delete 1, the paths that have to be considered are paths going from Qs to 2, right? So if we consider all paths going from Qs to 2, they would be labeled as epsilon followed by A star followed by a B. So we get QS, epsilon is empty string followed by an A star followed by B, that is through QRIP. QRIP here is 1. So a single transition labeled instead of with a single symbol with a regular expression, and the rest remains as is. If we had any other state that was that had a path to any state uh, that was connected from 1, we would have had to write regular expressions for those as well. Next we delete 2 from the state machine, and what we get is QS. So epsilon A star B is the same as, this is equivalent to writing A star B, right? So A star B followed by A or B the whole star followed by epsilon. So you have A star B followed by A or B the whole star because of the loop followed by an epsilon, which takes you from the dummy star to the dummy final state, and this is your final regular expression. So the regular expression turns out to be A star B A plus B the whole star. Alright, so this is a quick and short method to convert an NFA to a regular expression.